Hi, all right, welcome to the last class. Now we're going to talk about some work on semantic science. All right, this is a good quote here by Eric Baum and for a nice book called What is Thought from 2004. There's a real world with real structure. The program of mind has been trained on vast interactions with this world and so contains code that reflects the structure of the world and knows how to exploit it. This code contains representations of real objects in the world and represents the interactions of real objects. You exploit the structure of the world to make decisions and take actions. Where you draw the line on categories, what constitutes a single object or a single class of objects for you, is determined by the program of your mind, which does a classification. This classification is not random, but reflects a compact description of the world, and in particular description usefully exploiting the structure of the world. So what we're going to do is we're going to exploit structure of the world, in particular in terms of objects and relations, in order to make better decisions. So the overall thing I'm going to do today, I'll start off with motivation. I'm going to talk about ontologies, data, and the hypotheses. Okay, so the argument we're going to make for using probability is acting in the world is gambling. Whenever you act in the world, you're gambling on the outcome, because typically you don't know the outcome. And probability is the calculus for gambling. That's why we're going to use probability. Probability provides a calculus of how knowledge affects belief. Remember before, we wanted a lot of these times we're thinking about what should I do based on my belief. Well, probability tells us how we should update our beliefs. So here is our familiar Bayes rule. The probability of a hypothesis given the evidence is the likelihood times the prior divided by a normalizing constant. And often E is things like the images. But what if E is a patient's electronic health records? This contain their symptoms and their history. And H is a particular treatment on a particular patient. That's what you do. You say, here's everything we need to know about a patient. And H is the effect of a particular treatment, because that's what we want to decide in order to make an informed decision. So E here is a very complicated, heterogeneous thing. So everyone has a different electronic health records. And so we're trying to do that. What if E's electronic health records for all the people in the province? Well, then we'll find that's also what we want to use, because you want to not only use this patient, but all the patients in order to do something. And what if E is everything known about the geology of Earth? So what if E is more than that? It's everything about geology. So here's a motivating example. A patient walks into a GP's office, into a general practitioner's office, and you want to know what to do. So the output we might want is the top diagnosis, what's actually wrong with them. So this one might take into account what we observe about them, the utility, how serious things are. Suggested tests, what should I observe about, what we should try and observe about the world, what tests should we give the patient, and suggested treatments. And all of these have justifications. So that's the output we want. So let's think about what inputs might be relevant in here. Well, the obvious one is the patient's complaint, which in medicine is often called the reason for encounter. It's why they're in there. So they say, I have a sore foot, or have a bad cough, or have a fever. Then there's the observations, for example, by a receptionist who's not necessarily a doctor, so just describes in their own language what they're going to do. Doctors typically might observe other things and want to put those observations in. And then there's all the patient's history, their electronic health records, of everything they've done before, all their backgrounds and everything else, as well as all test results. And that's that's the inputs to this. But there's more inputs than that. In particular, there's the patient's preferences and utilities are also input to this model. So here we're going to have the preferences, what do people want, and what's changing over, and the utility. So what do they want? What are their trade-offs under uncertainty? But there's also, we need to worry about standardized vocabulary. And these are going to be called ontologies, the best practices about what's the right thing to do under different circumstances. We'd like to use the latest research results because we want to make sure that our recommendations are up to date and take into account everything that's known. So we want evidence-based decisions. And that includes data from every other patient is relevant to this, because how they went, how similar they were, and other things are important. And so we want to make a decision conditioned on all the information in the world in general. So everything else, everything around us could be potentially relevant, and we'd like to make an informed decision. So that's the goal here, is to make decisions based on everything you could possibly do. So let's have a look at what's the sort of problems we're going to get here. Consider predicting the effect of a treatment on a particular patient. Right, so what we're going to do, the information is heterogeneous. So it's provided by multiple sources at multiple points in time. So for example, from patient resource reports, what they claim, what someone observation, nurse or doctor has observed about them, lab tests, x-rays, and all sorts of information that's important in order to do that. And it's very heterogeneous. We sort of can't assume that everyone's the same, because they're not, because we don't have different information, different kinds of information about each person. It's often provided because it's unusual. So the reason someone gave an x-ray is because they had a symptom. So it's not provided at random. Someone doesn't tell you my head is connected to my shoulders because it's not an unusual thing to do. They'll tell you they have a sore arm or something else that's what's wrong with them. They wouldn't tell you necessarily everything. So they're providing information. Information is not provided at random. It's very rarely provided at random. It's also at multiple levels of abstraction. By multiple levels of abstraction, I mean in terms of more general or less general knowledge. So a broken leg versus a fractured leg. So a fractured leg is a type of broken leg. You could have a crushed leg, could also be broken. So we're actually here, we're going more, fractured leg is more specific than a broken leg. We also have multiple levels of detail, by which I mean in terms of parts and subparts. For example, a broken leg versus a broken femur, it's a different case, because a leg is part of a femur. So it's not a subtype of it, but rather it's a part of a leg. We have to really clearly distinguish between generality and parts. Similarly, if you consider predicting the amount of a particular mineral at a particular location, you get similar problems. And predicting whether a person would like in a particular apartment. Again, the information about apartments is heterogeneous, information about people is heterogeneous, and they actually tell us what's unusual that they want about an apartment, not they're saying that it has 4 walls, each room has 4 walls, or other things that are just details they don't care about. People typically don't specify for an apartment things that are not unusual. So this problem is inherently unrelational. There are many types of objects. There are patient, body parts, tests and infections, and relations. So lots of types of objects and relations. There is relational uncertainty, which means we don't know what's true. We can be uncertain about that. We can be uncertain about whether 2 descriptions refer to the same object or not. And we could be unsure about whether something exists or not. So there's all of these different forms of uncertainty we'll find. So we're going to interact with standardized vocabulary. SNOMED CT is a big medical ontology that has 350,000 medical concepts, and all of those are in multiple languages. So there's a lot of concepts in there that we can actually use for specifying things in a way that we're at least trying to be unambiguous. There's sparse data. For almost every pair of symptoms, or pair of diseases or disease treatment pair, no one in the world has both. So it turns out that there are about 100,000 different symptoms there. And 100,000 is interesting because the number of pairs is approximately the same number as the number of people on Earth. And so, but because of the long tail, most of these are unlikely. You essentially can show that from almost every pair, no one in the world has just those 2. So there's just not enough people to go around for all of the pairs of diseases. And so what's going to happen is that we can't learn the interaction amongst diseases from data. We need to make other assumptions about the world. There's actually lots of knowledge we can actually use, lots of expert knowledge and textbook knowledge. We should take that with a grain of salt because it can be wrong, because that's only just generalized from data as well. So the way that experts and textbooks get it is from generalizing